Now, some functions are difficult to integrate. So approximations sometimes is a better way of approaching it. The rectangle, we got better shape. See, if I was to draw a rectangle here, I'm going to have a huge overestimate. By making it a trapezium, instead of a rectangle, straight away I'm going to cut out a lot of that overestimate. Let's draw in that side. So there's our trapezium, called the trapezoidal rule, because in America they call a trapezium a trapezoid. I guess it's easier to say trapezoidal than trapezium. How would you say it? Trapeziumial. Yeah, anyway. So our formula for a trapezium, half the perpendicular height, which in this case would be b minus a, then the sum of the parallel sides, so the function value at a, the function value at b. What we saw with the rectangles was the more rectangles we did, the better the estimate. Well, the same thing's going to happen here. So if I drop in, I'll put it in the middle to make life easier. Again, I've now reduced that overestimate. There is our formula now when we add the two together, but we can do better than that because we've placed c in the middle. C minus a and b minus c is going to be the same amount. So I could factorise it out, whether I call it c minus a or b minus c doesn't really matter. But I'll end up with function a, but now I'll have twice function c because it's in both of them, plus function b. Alright, so that was with 2. What about if I split it up into 3 equal sections? And look, my overestimate now is getting really small. There it is. But again, we can do some factorisation because c minus a will be the same as d minus c, which will be the same as b minus d. And we end up with function a, twice function c, twice function d, twice function b. Because basically, the ones that are in the middle, we're going to get 2 because they're involved in 2 different trapeziums. So a formula we could write down. Yes, we know the exact amount would be the integral, but maybe it's an integral that's difficult to find, or maybe we just simply can't find it. We could estimate it with this, and the way I write it is this: y0 plus yn, so they're the end ones, and then 2 times all the other ones, that y others, for the sake of a formula. H is the height of our trapezium, which would be just one of these sections, and each one of these sections would be b minus a divided by however many of the trapeziums I've split it up into, so b minus a on n. If you want to keep a check on yourself, you should always end up with one more function value than you do the number of trapeziums. So the picture I've got here, I've got 4 function values but 3 trapeziums. Alright, let's use it to estimate this, and I've deliberately picked something we know the exact value of. So y equals 4 minus x squared to the power of a half. We are of course talking about our semicircle. Although I'm going from 0 to 2, so it'd be a quarter of a circle. How would the trapezoidal rule go? Well, they've asked me to do it with 4 intervals. Sometimes they call them intervals, sometimes they'll call them strips, sometimes they'll call them trapeziums, sometimes they'll call them subintervals, all sorts of different names. But basically we're breaking up into 4 sections. I know the width of each of my section is 0.5, so I will draw up a table of values. 0, 0.5, 1, 1.5 and 2, and work out the function value. They've asked me to do it to 3 decimal places. I usually carry through an extra decimal point in my calculation so I don't get rounding errors, and then I round off at the last stage back to the 3rd one. So I've taken it to 4 decimal places. There's my lovely formula. Another thing I like to do is just on top I go, right, I'm going to do 1 times the end one and then 2 times all the ones in the middle, just to remind me, yep, okay, these are the ones I'm multiplying by 2, these are the ones I'm multiplying by 1. So I'll substitute all that in, and I get 2.996. The exact value is pi, which obviously is 3.14. How good is my estimate then? Well, if I work out the percentage error, it comes out to be about a 4.6% error. Now obviously I could reduce that by increasing the number of trapeziums. There is an alternative way of setting it out. Right? So there was our table of values: 1 times the m1, 2 times all the ones in the middle. Bingo. There's the area. Notice what it does here. It's got 2 plus, it's still all the function values. 1 times the n1s, 2 times the ones in the middle. On the bottom of the fraction, it's just mimicking that pattern up the top here. So 1 plus 2 plus 2 plus 2 plus 1, and then we multiply it by the however far we're integrating. So I'm going from 0 to 2, so 2 minus 0. And if you do that calculation, yes indeed, it comes out to be the same amount. It's just a different way of setting it out. Let's look at this HSC question. Kenzo. Has anyone ever met someone called Kenzo, by the way? Not where they came up with this name, Kenzo. I've never heard of that name. Anyway. Driving car along the road, his friend recording the velocity of the car in kilometres per hour every minute over a 5-minute period. Here's our table of values. They want to find the distance covered, but to help us out, they've told us it is the integral. And the reason it's the integral of that, velocity is the rate of change of displacement or distance with respect to time. So if you want to find the distance, it's like finding the primitive function of the velocity. It's that integral. We don't know the function vt, and that's why we're going to use the trapezoidal rule. So we can estimate using this table of values. They want us to use it. Oh, there it is, 1 decimal place. They're interested in the accuracy. Okay, there's the table of values. There's my formula. I'm going to do 1 times the n1, 2 times all the ones in the middle. Subbing it in. So the width is 1/60th, everyone's 1/60th apart, and we come up with 5.4 kilometres. If I was to use the alternative setting out, there it would be. So it's our function values times the appropriate ones. On the bottom, 1 plus 2 plus 2 plus 2 plus 2 plus 1, and then the final bit is the overall width, and so we were going from 0 to 5 on 60. And amazingly, it comes out to be the same amount. Okay.